So what is quantitative analysis? Well, start off with, quantitative analysis is basically things that we can measure or calculate amounts of or concentrations. So as you can guess, we're dealing with quantities of different substances. Rather than just, what substances are present and what their structures are, we're looking at measurements of substances. So we're measuring things like amounts and concentrations. So how do we look at amounts and concentrations from a chromatogram? Well, basically the way we do it is we look at one crucial rule. Basically, quantitative analysis of a chromatogram revolves around the idea that the concentration of a specific compound within a mixture that we're sampling to produce a chromatogram, the concentration is directly proportional to the area under the peak that was caused by that substance. So if we have, for example, a certain compound, call it compound A, in a mixture, then its concentration is going to be directly proportional to the area under the peak that has been identified as being caused by compound A. So let's say we've got a chromatogram here. Then the best way for us to do this is, let's say we've got our chromatogram. Like that. Let's say we've identified what this substance is. That substance there, the substance causing this peak. Now we know that the concentration of the substance that caused this peak is proportional to the area under this peak. So the best way for us to figure out the concentration of this substance in the sample that we use to create this chromatogram is to create a graph that looks a little bit like this. If we could somehow get a graph of concentration, just abbreviate that there, so concentration versus the area under the peak. Now this graph, because they're directly proportional, should be a pretty straight line like this. So that's a straight line there. It's a directly proportional relationship. And so if we can somehow obtain a graph, this graph revolving around the substance that we're dealing with in this peak here, then all we would have to do would be to measure the area under this peak, plug it into this axis here, and then just figure out from the graph the concentration of the substance that caused this peak. So that's all we want to do. We want to somehow obtain this graph. And so the way that we obtain this graph, so obviously this graph needs to be representative of how area and concentration are related in specific conditions, or with a certain column and at a specific temperature with specific stationary and mobile phases. That's how we need a graph for the area versus concentration under those specific conditions, the same conditions that we use to produce this chromatogram. And so the way that we do that is we run standards. So obviously here we want to know how area and concentration affect one another. So what we do is we run standards of known concentration. That is how we do it. And so we run maybe 3 or 4 of these standards, so we can get 3 or 4 points on this graph, and then we can rule a line and sort of complete the graph through the points that we've plotted. And from there we can just use this data, use the height of this peak to figure out our concentration. So let's say I've been experimenting with a few different types of petrol. And so I've done a chromatogram. Just do this in a different color. So this is my chromatogram test. I've been experimenting with a few different types of petrol to see which petrol is the best. Now I've identified one petrol as being the best, And so I want to analyze it a little bit. And so let's say I've put a sample of this petrol through a chromatogram like this. And I've produced a chromatogram that looks like that. So I've got about 5 different substances in here. Now, basically what I want to do is I want to figure out the concentration of a substance called benzene. Now, benzene has a chemical formula of C6H6. So I've figured out that this fuel here is the best performing. I've tested it, and now I want to know how much benzene is in it, so I can try and reproduce this fuel and make lots and lots of it. So I've got some benzene here, and I want to figure out what its concentration is in this sample. So I've identified, first of all, that this peak here is the peak, this tall one, is the peak produced by benzene. So that is the benzene peak. And so I can work out the area under this peak just by looking at it and making a graph like this and plugging it into a graph like this. But first I need to create this graph. So what we're going to do is we're going to run standards of known concentration. So we know that, let's say this has a retention time of 6 minutes. So what we're going to do, we've got 4 different samples containing of pure benzene at varying concentrations. Not pure benzene, obviously, if we're dealing with concentration, but of sort of a mixture containing simply benzene and a solvent. So let's say I've got four samples here. I've got this one here. Now we know that this one has been made using benzene with a concentration of 0.4%. Now, obviously, there's lots of different ways to express concentration. We can have percentage concentration or percentage by mass or molar concentration or all those sorts of things. However, it's important to be aware that no matter what sort of unit concentration we use, this graph will still be linear. It'll simply be its gradient that will change as we change the unit of concentration. So we've got this, we've produced our chromatogram. We come up with a height like there at a retention time of 6 minutes. And so let's say that this height here, it's a retention time of 6 minutes, it's a 0.4% sample. It has a height of 0.6 centimeters. Now, obviously, these peaks that we're dealing with in this sort of situation are often very thin. And so when they're all thin and you can't really measure their width or the area, it's a bit abstract to measure their area, we can simply measure their height when they're all extremely thin like that. So and that way we can just plot concentration versus height and we'll still get a pretty accurate result. So often that's how we're going to be dealing with things, because these peaks are simply just lines up rather than big triangles like that. So it seems it's a bit difficult and a bit senseless to try and calculate the area. So we've got a 0.4% sample and it's produced a peak size of 0.6 centimeters. So now we've got 2 other samples here. Concentration and area. Again, we're going to have another peak after 6 minutes. And this is our 1.1% sample. So what happens here is we get a pretty big peak at 1.1%. So that is our peak when we use a 1.1% sample. And this gives us a height of 1.65 centimeters. So 1.1% produced a peak height of 1.65 centimeters. So we'll do one more sample. So here again, we've got concentration and area. We get another peak at 6. And we'll say that it's about this high. So this is our 0.8% sample. And here, this 0.8% sample produced a peak height of 1.2 centimeters. So I'm not drawing these these graphs to scale. I'm trying to, they're mildly to scale, but not exactly to scale. So this is just the data that we've obtained when we've run these 3 chromatograms. So we've got 0.4% and 0.6 centimeters tall, 1.1% and 1.65 centimeters, and then 0.8% and 1.2 centimeters. So let's create some room up here to create our graph. So if we have our graph looking a little bit like this, we've got concentration and area. Apologies, these 3 smaller graphs down here, these are not graphs of concentration versus area. So they should not have these A and C here. These are, just like this graph, they are all about time and recorder response. So these should not have C's or A's around here. On the vertical axis of all 4, this pink one and the 3 green ones, they are all recorder response, and on the horizontal axis, it is always time for these graphs. Up here, however, we are dealing with area and concentration. So if we plot these 3 sets of data here, so we've got, so we know that at 0.4%, we had a height of 0.6 centimeters, which we'll put there. And then at 0.8%, we had a height of 1.2 centimeters, so twice as high there. And then at 1.1%, we had a height of 1.65. So this is our graph. So now if we rule a line through our 3 points, bit of a rough line here, but it is a straight line. So we rule a line through our 3 points like that, and we have a graph of area versus concentration under the conditions that we've used here. Now, if we label our graph a little bit better, we have 0.6, 1.2, and 1.65. And obviously, because it's a bit difficult for actually measure area in this case, we've in fact dealt with height, capital H, and this is in centimeters. We know that that's in centimeters. Here our concentration is 0.4%, 0.8%, and 1.1. So if we put in brackets here, now this percent is a percentage by mass. However, as I said, if we used other units of concentration, we'd still have a successful method. So height is in centimeters. Now, what we're looking at here, so that's 1.65 and 1.2. So what we look at here is our actual chromatogram of our fuel sample. Now we want to know how much benzene there is in there. So what we're going to do is we're going to measure the height and see where it fits into this graph. So let's say that we look at this height here and we come up with 1 point, sorry, wrong color, 1.42 centimeters. So let's say that this peak here is 1.42 centimeters tall. We measure it, we get this data here. So what we're going to do is we're going to use this graph, we're going to interpolate between the data points we've already got. So it means we're going to use the line that we produced from these 3 points that we've plotted to work out the percentage of concentration. So we've got a height of 1.42, so that's halfway between here. Now if we rule over to the middle, then we see that at 1.42 centimeters, this is where the graph is. So if we let the height equal 1.42, then we can rule and see that the point on the graph with a height of 1.42 centimeters is here. So now if we rule down, we can see that it's halfway between 0.8 and 1.1. So that tells us that we're dealing with a fuel sample with a concentration of halfway between 0.8 and 1.1, 0.95%. And obviously it's very important in all of these situations, both when you're running these chromatograms and creating this graph, to create a thorough scale. So we want to make sure we measure it out properly like this when we're doing it. So every dash there is 0.1%, and so we want to make sure we create a really thorough, a really good tight scale so that we can, when we do this method at the end, when we use our height of our fuel sample to plug into our graph, so that we can get very accurate results. So here we can see fairly accurately that we have a concentration of 0.95% for this sample, and so that is the concentration of benzene or C6H6 in my fuel sample. So that is our final answer. And so that's how we have to use multiple standards of known concentrations of the substance that we're analyzing. We have to run them through the same chromatogram, so we can produce this graph, height versus concentration, for that column. So we're running these through the same column. That way we produce this graph for those specific conditions. And we can use this data, which was collected under the same conditions, in combination with this graph to find out the percentage concentration, or any sort of concentration, depending on what we've used here, of, in this case, benzene in our fuel sample.